Welcome to StudyKwik. Today we'll learn about the Air Data Computer, ADC. The ADC replaces individual pressure instruments with a centralized source of data. It provides electric or electronic outputs for modern aircraft. Each static instrument had its own line. Pitot instruments had pitot and static lines. A typical system required 15+ pitot-static lines for multi-crew aircraft. This led to duplication, complex piping, and potential leaks or blockages. Early analog ADCs solved this by requiring just 3 inputs: pitot pressure, static pressure, and total air temperature. Electrical power was also required, with a standby power source added later. The computer converts static pressure into altitude and vertical speed. Pitot and static inputs allow calculation of indicated airspeed. Higher manufacturing tolerances make the instrument error minimal and correctable. Position error is also accounted for, giving calibrated airspeed, CAS. Total air temperature can be converted to static air temperature automatically. The ADC now has all it needs to compute true airspeed and Mach number. From the 1980s, angle of attack, alpha, was added as an input. This allows safe, low-speed flight, particularly on approach, without correcting for weight changes. Modern ADCs still rely on pitot, static, total air temperature, alpha, and power. Early analog ADCs passed pitot and static pressures through tubes to pressure capsules. Capsules attached to an I-bar, pivoting to produce movement relative to an E-bar. This out-of-balance signal was amplified and sent to a servo motor to turn a shaft. A transducer converts a physical measurement, like pressure, into an electrical signal. Later, transducers were placed near sensors to reduce long piping dependence. Total air temperature was already an electrical signal from a temperature-sensitive resistance. These transducers are often called interface units. With digital ADCs, they are termed analog to digital interface units. Transmission becomes a digital data bus, not an analog electrical signal. Modern ACs incorporate angle of attack inputs and provide data from multiple systems. They are usually off-the-shelf units, compatible with many aircraft types. Each aircraft has a unique position error and K-factor, handled by a configuration module. Many modern ADCs include a built-in test, BIT function. 3 operating modes: startup, power-up, continuous operation, and maintenance BIT. Continuous BIT checks the system roughly once per second during flight. The ADC provides a central source of information for multiple instruments and systems. Older aircraft may have analog displays for airspeed, Mach, altitude, and VSI inputs. Pitot-static, total air temperature, alpha, weight on wheels detector, and power supply. Outputs go to flight data recorders, EFIS, direct reading indicators, and alarms. Mach and CAS/IAS are displayed digitally or via traditional indicators. Altitude data is sent to altimeter displays, barometer alerters, and height encoding transponders. VSI receives vertical speed outputs, also fed to EFIS. Overspeed and underspeed warnings are included. The stall warning system is decoupled on the ground, using the weight on wheels switch. Other users include inertial reference systems, flight control computer, and FMS. The ADC provides digital air data to multiple systems, reducing the need for complex piping. Advantages of ADCs: improved displays, reduced instrument error, and reduced lag. Mechanical friction and design errors are minimized with electronic systems. Configuration modules correct for position error and K-factor. The ADC calculates TAS, Mach, and static air temperature accurately. It allows a clean, centralized system, easier maintenance, and reduced piping. Failure warnings compare multiple ADC outputs and alert pilots to discrepancies. Summary: early analog ADCs solved complex pitot-static networks in the 1950s. Digital ADCs from the 1980s onwards are standard on modern airliners. 5 main inputs: pitot, static, total air temperature, angle of attack, and power. Data transmission evolved from tubes to electrical signals to digital buses. The configuration module handles aircraft-specific errors, ensuring accurate readings. Built-in tests provide startup, continuous, and maintenance diagnostics. The ADC is central to modern flight systems, improving displays, reducing error, and providing failure warnings. It simplifies design, reduces piping, and supplies multiple instruments and systems. Electronic ADCs are reliable, accurate, and essential in modern aviation. Thank you for watching StudyKwik. Don't forget to like, share, comment, and subscribe for more aviation lessons. Keep learning and fly safely.